Hello everyone. Though this is let's say an introduction before making the exercise concerning the heated or the cooled hot bar. So we have two examples to solve: the ball exchanging through radiation and through convection. So before attacking the examples, I want to explain for you some basics about heat transfer. So that's why I would like to start with this point. So thermal energy and heat transfer propagation. Thermal energy transfer is heat moving from a warmer object to a cooler object. This is known as thermal energy transfer. We know all in thermodynamics that heat moves from hot bodies to cool bodies. So the heat transfer moves through conduction, convection, and radiation. Heat can be transferred in three different modes: conduction, convection, and radiation. All these modes of heat transfer require the existence of a temperature difference, and all modes are from the high temperature medium to lower temperature one. Okay. So if you take, for example, a candle, heating a metallic rod or a rod in general, or a spoon immersed in a boiler or immersed in a recipient, in a cooking recipient, you will have this sentiment of uh, uh, yeah heating in time. Because why? Because heat transfer moves through using the conduction phenomena through the spoon or through the heated rod. Now, concerning the convection, if you heat your recipient, recipient filled with water, you will see after a certain time that all the water in this recipient become hot. In fact, what happens is that the fluid, which is the fluid, the water or the milk, or I don't know, will be in contact with the lower level of the recipient, which is heated. So it will take some calories and go up and make this kind of recirculation as is shown in this animation. So the food particles take the heat and go up because it would have less density. So, and you will have this kind of vortices, and this phenomenon of heat exchange is called convection. The third form of energy transfer or heat transfer is the radiation. So if you take a halogen ampoule and you switch it on, and you put a thermometer at a certain point, even with no conduction or convection, you will have an increase in temperature. Why? Because there are some the third form of energy transfer is in form of infrared waves that are moving even in vacuum and touch the thermostat. And it is like this between sun and earth. Sun gives heat in form of radiation, and this radiation waves go through the vacuum and finally arrives on the Earth's surface. So in reality, there's a competition between the three modes. You have the convection here through this rod. You have a convection because heated air will go up because it has less density. So this man will have the sensation of warmness. Same thing if you are sitting here horizontally. In general, there's no convection in this direction, but there's a transfer through infrared radiation. Okay, and you will get this sensation of heat. So if I want to resume, conduction is the transfer, or to define correctly, conduction is the transfer of energy from the more energetic particles of a substance to the adjacent less energetic ones as a result of interaction between the particles. Conduction can take place in solids, liquids, and gases. In gases and liquids, conduction is due to the collision and diffusion of the molecules during their random motion. In solids, it's due to the combination of vibrations of the molecules in the lattice and the energy transport by free electrons. So, as in this example of a heated rod, or in this example of a brick wall, you have a chamber here at 20 Celsius, and you have here the outside in winter, which is cold at 5 Celsius. You have you need all the time to warm your chamber because there's a loss of energy through the wall by conduction. Oh, for the heat transfer by convection, so the convection is the mode of energy transfer between a solid surface and the adjacent liquid or gases in this motion, that is in motion, and it involves the combined effects of conduction and fluid motion. The faster the fluid motion, the greater the convection heat transfer. In the absence of any bulk fluid motion, heat transfer between a solid surface and adjacent fluid is by pure conduction. So if you look at this example, or in this hot block with air circulating at the surface, you have this phenomenon of convection. In this case, we have two kinds of convection. The natural convection, when you have air or a fluid near a heated surface, you will get this natural circulation due to the difference of density between cold and heated air. And here you have the forced convection, when you have a fan or you have a wind blowing on this body or this egg, you will exchange more and more energy, and this is called forced convection, and here you have natural convection. So the heat transfer by radiation is the energy emitted by a matter in the form of electromagnetic waves as a result of the changes in the electronic configurations of atoms or molecules. Unlike conduction and convection, the transfer of heat by radiation does not require the presence of an intervening medium. In fact, heat transfer by radiation is fastest. Why? Because you transfer energy with the velocity of light. So in this case, in the case of this chicken heated in the microwave, or for this person in front of this fire, or for the case of the planet Earth heated by the sun, you have a problem of radiation. It is as simple as this. Now let's move to our examples. The first example is the example of a metallic sphere ball heated at 2000 Celsius using a resistor. Sometimes you close the resistor and you increase the temperature until it turns 200 degrees Celsius, and you aspire, you run the vacuum pump to create a certain vacuum here. It's not pure vacuum, it's an industrial vacuum, but it is sufficient to minimize the convection phenomenon and the conduction phenomenon. And this chamber, vacuum chamber, is at T equal to 20 Celsius. So this sphere have a radius of 2 centimeters, a volume like this, a surface, a density 1,200 kilogram per cubic meter, a capacity of 1,000 joule by kilogram by Kelvin, and we want to solve the transient heat transfer problem, the temperature evolution through time of this ball. So for this reason, let's calculate the energy balance for this ball. So energy balance for the ball between T and T plus dt. So delta Q, which is the energy loss of this ball, is equal to its mass cross its capacity cross delta T or dt, which is the temperature at the time T plus dt, minus the time at the temperature T, which is equal to, if you convert the mass into rho v, you will get, and T plus dt minus dt to dt, you will write rho vc dt. So this energy lost is lost by radiation. So that's why we will write that this energy, this heat loss, is equal to minus radiative flow, minus because it's a loss, cross dt. This is a heat flow which is in watt. And this heat flow can be written like this. Flow radiative is equal to sigma, which is Stefan Boltzmann constant, cross A, which is the surface of the sphere, because we exchange through between the surface of the sphere and the word. So the sphere of space is equal to A, which is equal to A or S. Maybe here it is better to change it to A. Okay, I will change it to A. Right. Okay. So this is the radiative flow, sigma A, which is the surface. I change it here with A. Okay. T exponent 4 minus Ta exponent 4. So this is how heat transfer is done through radiation. So the temperature here must be in Kelvin, or otherwise you will get an error. So finally, now if you make this equality, you will have rho Vc dt equal to minus sigma A T exponent 4 minus Ta exponent 4 dt. So which leads to this differential equation, dt by time, okay, minus sigma A divided by rho Cv T exponent 4 minus Ta exponent 4. So you can take all this term and you write like that rho Vc rho Cv divided by sigma A is called T lampet, or the aggregate capacitance, which is a time constant. And you would write that dt divided by t is equal to minus t exponent 4 minus ta exponent 4 divided by t to input. So you have this kind of differential equation, and you solve it using MATLAB as it is mentioned in the video after. Now, this is for the first example. So if you have a pure radiation problem, you will get this for the sphere. Okay, with a T lampet for radiation, rho Cv divided by sigma A. So rho for the volumic mass, C thermal capacity, V volume of the sphere, sigma Stefan Boltzmann constant, A the surface of the sphere. So you will get T divided by T equal to minus T lampet T exponent 4 minus T exponent T of at time equal 0 equal to T0. Okay. Let's take now the example 2, the cooling ball through convection. Now there is no radiation, we will neglect the radiation, which is not really rigorous, but it is just to make the exercise. We take only convection in this exercise. So we have an air flow through fan. We have a temperature of this air of 20 Celsius. H, the convection coefficient, is equal to 20 watt by square meter Kelvin, and these are the characteristics of the ball. The ball is left at time t equals 0 at the temperature t equal to 1000 Celsius. Let's make the energy balance. So the energy balance between the time t and t plus dt, you have delta Q, the loss of energy, is equal to mass cross the thermal capacity cross t at time t plus dt minus t at time t, which is equal to rho Vc dt. Now this loss of energy is due to convection. Okay, the convection occurs when you have this cool air touching the surface of the sphere, it will rush, it will take some calories from the surface, and this exchange is called convection. So in convection, you have H, a coefficient of convection, cross the surface of the body, cross T of the surface minus T of the air. Okay, so it is like this. So we will write that delta Q is equal minus flu, which is in what? View of convection, cross dt. And by making the equality between the two, we have the energy balance like this. Okay, and finally we can write that the temperature decrease of the ball as a nodule like this. dt divided by T is equal to minus HA divided by rho Vc, T minus Ta, which leads to, if you write that tau ampere is rho Cv divided by HA, now you have H instead of sigma. So you have to take care of this. Okay, otherwise you will get a problem. So now your differential equation, it is not really similar to that one given in the exercise of the radiation. Here you have T minus Ta. So that's why here you can do your job using the values of temperature in Celsius, no problem. In reality, we will in thermodynamic and heat transfer we work all the time in Kelvin. But if you have such kind of problems, you can work in Celsius, and there's no problem. Now, if I can go back for in the radiation here, if you do it in Celsius, here you will get an error automatically. So thank you for watching and goodbye. So hello everyone, this is the first example, cooling ball through radiation. So we have this ball heated at TO at time equals 0 to 100 Celsius. We have a vacuum pump to create an industrial vacuum here to avoid any conduction or convection of heat transfer between the ball and the recipient or the vacuum chamber. The temperature of the vacuum chamber is almost 20 degrees Celsius. So after solving the heat exchange balance, we have this differential equation. This is a fourth order differential equation. So the first derivative of time over of temperature over time is equal to -1 divided by 2 lambda, which is an aggregated capacitance. Temperature of the ball exponent 4 minus Ta, which is the temperature of the rigid vacuum chamber, the limits of the chamber, exponent 4, which is equal to 20 Celsius. I have to notice here that we have to work in that case in this case in Kelvin. So everything written in Celsius you have to be converted in Kelvin. Otherwise you will get problems and will have false results. So every time you will work in thermodynamics and you have radiation, work in Kelvin and you are okay. If you are working for convection or conduction problem, the problem will not appear. But in general, for this kind of for nonlinear situations, it is better to work in Kelvin. So that's why we will try to convert all the values we have as the temperature 20 or 2000. We will add to 273 to be in Kelvin and to get good results. So this is our differential equations. We go to MATLAB. We write clear all. So this is our script. Clear all, close all, CLC. The TO here is equal to 2000, which is the initial temperature of the body, the T equals 0 of the ball. So we add 2073 to be in Kelvin, and we solve the differential equation. We have to create my function radiation, which is all this second member. We have to write a function for this, and we'll call it in ODE 45. And from t equals 0 to t equal to 1000 seconds. And the initial value for the temperature is T0. So if we write, as I want to remember you, if we write something like this between 0 and 1000, so we give the solver the possibility to choose itself the time step. And we can force him by adding h here, okay, time step h. At the end, after calculating, we plot, but I subtract here 2073 to be in Celsius. Okay, so let's take a look at my function radiation. So this function, it is like this. So dy is my function radiation of t and y. The radius of the ball, as it is explained, is in the problem is 2 centimeters. So 2 exponent minus 2. The rho, which is the density of the material, is 1200. Sigma, which is the Stefan Boltzmann constant, is equal to 567 10 exponent minus 8. The volume of the sphere, V, the capacity, the calorific capacity in joule by kilogram by Kelvin of the material. The A, the surface of the sphere, 4 pi R2, and the ambient temperature, which is the temperature of the vacuum chamber, which is equal to 20 Celsius plus 2073. And like this, we can calculate the total ampere, which is equal to rho Vc divided by sigma A. Rho V is the mass, C is the capacity, sigma is the Stefan Boltzmann constant, A is the area. So we write Ty is equal to 1 minus 1 divided by 2 ampere, okay? Y exponent 4 minus Ta exponent 4, and Ta is in Kelvin and Y might be in Kelvin. So like this, we run our script and we plot. I subtract here 2000 to be in Celsius. So this is my result. So after you look, after from 200 Celsius, after 1000 seconds, we have a temperature about, let me make a small zoom, okay, near what? Near 75.5 Celsius. So this is how to solve our radiation problem, okay? So imagine now you want to solve the convection problem. The convection problem is a little bit different. We don't have a vacuum chamber and the exchange is done. So you have a fan and the exchange will be directly between the air, okay, the airflow, and the ball, the same ball, heated to 2000 Celsius. So we have an energy balance delta Q between time t and delta t, which is equal to mc, maybe I can enlarge this, which is equal to mc t at time t plus delta t minus t, temperature at the time t, which is equal to rho v, which is the mass, capacity, c, dt, which is the temperature at time t plus delta t minus the temperature at time t. So now this loss of energy in the ball is equal also to the energy exchanged by convection between the ball and the air, which is in contact of with this heated surface. So because it is a loss, we add a minus. So delta Q is always equal to minus phi convection that multiplied by delta T dt, which is the time. This is the power. Okay, this is the heat rate loss in power. So it is in watt. So the flow of convection is equal to H, which is the coefficient of convection between the air and the heated ball. A, the surface of the ball, which is 4 pi R2, and the temperature of the ball at the time t minus Ta. We suppose in this exercise as in a radiation exercise, that all the ball have an homogeneous temperature of T, which is a good approximation if the ball is small. So let's look at the differential equation. So if we simplify, at the end we have something like this, and we can write it in this form: dt divided by t, okay, is equals to -1 divided by t lambda, t minus t air, okay? And at the time t equals 0, we have a temperature equal to T0, which is equal to 2200 Celsius. For the case of convection, pure convection problem, in difference with radiation problem, convection or conduction, you can work directly in Celsius. There is no problem. Why? Because you make a difference here and you make difference here, so the 2073 will disappear. Otherwise, if you have a radiation problem, you have to take care. You have to work in Kelvin, and after this, you convert in Celsius. Okay? So you have this differential equation. You can end this script. So you can go to the script of the convection. It is mainly the same script. I did not add 2073 here because there is no obligation for this. Maybe I will do it in green. Okay. So ODE 45 at my function convection from 0 to 1000. And the temperature, initial temperature of the ball is T0. I save. My convection, it is mainly the same thing, but here you have dy equal to minus y minus TA, which is equal to T air. Maybe I can write T air. Okay, T air here. Okay, but it's not the same T lambda as in radiation. Here you have rho Vc, okay, but here you have HA. In the other example, you have sigma, which is the Stefan Boltzmann constant. So this is the structure. It's very simple. It's very easy. If you run now your script up, you have, so at time t equal to 1000, you have a temperature of maybe around 40. I can zoom here. Okay. So at time t you have mainly about maybe 34.8 or 35 Celsius. So as you see, in general, convection exchange is more important than radiation, but it have to be taken case by case. Why? Because what condition this is the quantity tau lambda, okay, which is a time discharge time. If this quantity in convection and in radiation have the same order of values or are equal, you will have the same results. It is as simple as this. Okay, so now you have, this is a problem for convection. I showed you the problem for radiation. In general, you can have a combination of the two problems. You can have almost conduction, convection, and radiation, and you can solve it by solving this kind of ordinary differential equations. Thank you very much.